Hello, welcome back to Mystery Science. Yesterday's video, I left you with 4 questions from the Starshine chapter of the Pearson EdExcel A-Level Physics 2 book by Miles Hudson. These questions are on page 175 if you are following along in the textbook. If you want to grab a copy of that textbook, please have a look at the affiliate link in the description section. Right, so these are the questions I left you with. Number 1, what is the luminosity of the star Sirius, which has a surface temperature of 12,000 Kelvin and a diameter of 2.22 million kilometers? Question 2, the sun's surface temperature is measured as being 5,800 Kelvin. Calculate the peak wavelength of the solar spectrum. And B, the peak wavelength from the sun is in fact measured on Earth as being 470 nanometers. That's not going to have been what you got for 2A. The question is, why not? Question 3, calculate the peak wavelength output we'd expect of Bellatrix if its surface temperature is 21,500 Kelvin. And then I showed you the graph of Rigel and Canopus and the sun with their peak wavelengths, and you were tasked to find the temperatures. So let's get stuck in. So question 1, what is the luminosity of Sirius? It's got a temperature of 12,000 Kelvin and a diameter of 2.2 million kilometers. So we start out by finding the surface area. Now, A-level being A-level, it likes to trick you, and you have to look very closely at the units. Please notice that it's not 2.2 million meters, it's 2.2 million kilometers. Also, it's the diameter and not the radius. So if you're doing 4 pi r squared as your surface area, you can obviously substitute in d, but it becomes very tricky. We have to look at what the radius actually is. So in meters, that's 1.11 times 10 to the 9 meters. And that gives you an area of 1.55 times 10 to the 19 meters squared. We substitute this into the Stefan-Boltzmann equation. The luminosity is given as the Stefan-Boltzmann constant multiplied by the surface area multiplied by the 4th power of the temperature. So we simply plug in all of those numbers. 5.67 times 10 to the minus 8 times 1.55 times 10 to the 19. So I'm used to saying 1.6 times 10 to the minus 19 so much. Times 12,000 to the power of 4. And this gives you a luminosity of 1.82 times 10 to the 28 watts. So if you compare that with some of the wattages of the stars that we looked at in the previous video, you can see that Sirius is quite a bright star, which is not surprising given that its temperature is 12,000 Kelvin and it's pretty darn big. Alright, so question 2, part A. The sun's surface temperature is measured as about 5,800 Kelvin. Calculate its peak wavelength. And this is simple. We just use Wien's law, and we use the Wien constant, which is 2.898 times 10 to the minus 3. And that's the temperature multiplied by the peak wavelength. So now we simply divide Wien's constant by the temperature. And then we can calculate the peak wavelength. In this case now, the peak wavelength is 500 nanometers. And the answer, why is our measurement not 500 nanometers from the Earth? And that's because we have atmospheric absorption. We're looking at the sun through an atmosphere. When we look at the sun, it actually appears yellow, and that's because some of the spectrum is being absorbed. The sun isn't as yellow as it appears on the Earth. If you go out into space, it's whiter in color than we see. So the atmosphere is absorbing some of that spectrum and dispersing it all over the place, hence why the sky is blue and etc. And so that changes our reading somewhat. Okay, calculate the peak wavelength output we would expect if Bellatrix if its surface temperature is 21,500 Kelvin. Again, we just use Wien's law. We take the Wien's constant. This time, again, we divide by the temperature. It's exactly the same equation, exactly the same thing. And now we get a peak wavelength of 135 nanometers, which is much smaller than the sun. So we'd expect that to be much, much hotter, which it is. And then finally, calculate the temperatures of Canopus and Rigel. Now this depends very much on how you read this graph, and normally there will be probably a 10% tolerance in the reading of the graph. So be very careful when you look at the graph. The examiners will have a list of answers and a range of answers that they will accept from you. But if you can, try and be precise. So if this was an exam question, get a ruler out and measure the distance between each 100 nanometers and try and figure out exactly where those peak wavelengths are. Okay, so if we look at Canopus, what is the surface temperature? So again, we use Wien's law, we use Wien's constant. I've taken the wavelength, the peak wavelength, to be 490 nanometers. So we just plug that into the equation and we end up with a temperature of 5,920 Kelvin. And now we do exactly the same thing for Rigel. Here I've used 275 nanometers and you end up with a temperature of 10,500 Kelvin. Alright, thank you very much. I've been Mr. E and this is Mr. E Science. That was just a very, very short video answering some of the questions from the last Starshine video. Over the next few weeks, we will be looking at more of this space topic from the A-level. If you have any questions or if there's anything you want me to cover in any specific order, we'll be doing the space topic now. After the space topic, I have no particular order in which I'm going to do the videos. Would you like me to start from the year 12 content right the way through, or would you like me to go through the year 13 content? You let me know, please, because otherwise I'll get distracted by doing Key Stage 3 and Key Stage 4 work. So I want you guys to get as much out of this as possible. Alright, check out the playlists and check out me opening Pokemon. Check out any of the affiliate links down below and stay safe. I will see you soon.